When a metallic turbine blade warps and shatters under immense operational pressure, the mechanical failure is chaotic, rapid, and entirely nonlinear. In standard structural engineering, idealized linear models work perfectly well for calculating basic static loads, like the resting weight of a stationary bridge deck. But operating environments are rarely static or perfectly linear. They involve extreme temperature variations, violently shifting forces, and the slow accumulation of material fatigue over thousands of hours. When a physical structure faces these compounding variables, simplified mathematical assumptions break down. They assume small, predictable responses in scenarios where reality dictates severe, chaotic reactions. Relying on those simplified computational models in extreme environments results in deep predictive failures, allowing catastrophic structural collapses to occur in the physical world before they are ever caught on a computer screen. To prevent this, an engineering simulation must precisely account for the overlapping complexities of the physical world. This is the domain of ADINA, Automatic Dynamic Incremental Nonlinear Analysis, a premier finite element analysis software suite. Its core directive is to unify dynamic forces, shifting geometries, and multiple physical properties into a single computational environment. Researchers and engineers utilize this architecture to accurately predict complex structural behavior, running exhaustive high-stress scenarios long before a physical prototype is ever cast or machined. By processing these overlapping physical variables simultaneously, ADINA resolves the technical friction between mathematical complexity and practical predictive engineering. Consider the necessary steps for verifying the structural integrity of a complex mechanical gear assembly. This 3D wireframe illustrates the first step of finite element analysis, translating physical geometry into a mathematical mesh. Using ADINA's element library, engineers assign specific finite elements. Simple supports become 1D beams, while load-bearing gear teeth convert into dense, faceted 3D solid element grids. With the geometric mesh established, the next critical step is defining the exact material properties of that framework. Metals, plastics, and composites do not react to mechanical stress in identical ways. They require highly distinct mathematical parameters to dictate how they stretch, compress, and ultimately fail. ADINA supports a vast array of material models to process this, ranging from basic linear elastic parameters for stiff metals to complex viscoelasticity for rubbers and polymers. Assigning a plastic material model dictates how the software calculates permanent deformation once a component is pushed past its normal yield strength. Pairing a highly accurate geometric mesh with these precise material definitions forms the foundation for running a viable structural simulation. Standard analysis runs into a hard mathematical limit. It assumes deformations remain small and strictly controlled. This graph compares theoretical projections against reality. Real-world forces cause large deformations. A structure will stretch or bend so severely during an event that its baseline geometry changes entirely. While a linear projection moves infinitely upward, the true physical reaction follows a curve that flattens out, demonstrating plastic deformation. To track this accurately, ADINA utilizes advanced nonlinear algorithms that continuously recalculate the structure's overall stiffness as it deforms, monitoring the shifting material properties in real time. That complexity escalates exponentially when two separate objects inevitably collide or grind against each other, entering the realm of contact mechanics. Looking at this microscopic cross-section of two gear teeth grinding together, we can see the mathematical difficulty. The software must calculate intense friction and wear along the boundary without ever allowing the interacting meshes to pass through one another. ADINA's robust contact analysis algorithms are engineered specifically for this, accurately modeling surface friction and physical component wear under heavy, repetitive loads. These nonlinear capabilities ensure that the underlying numerical solvers remain completely stable, even as the simulated geometries warp, clash, and severely deform. Of course, structures do not exist in a vacuum. They are constantly subjected to moving, rapidly fluctuating forces from their physical environment. Through dynamic analysis, engineers can simulate sudden external shocks, tracking the exact response to rhythmic machinery vibrations or the violent, chaotic shaking of a seismic event. ADINA processes these impacts using highly specific tools, including modal analysis, time history tracking, and frequency response algorithms. But the final layer of real-world complexity is that physical variables do not wait their turn. Mechanical stress, extreme temperatures, and fluid dynamics often occur simultaneously. This schematic of a mechanical valve illustrates coupled multiphysics analysis, the simultaneous calculation of interacting phenomena. As fluid moves through a valve, it creates immediate thermal gradients. Immense heat, whether generated by internal pressure or ambient environment, rapidly warps the structural integrity of the surrounding metal. ADINA tightly couples the fluid flow, thermal spread, and structural deformation together. A sudden pressure spike in the fluid immediately triggers a recalculation of both the thermal load and the physical strain on the metal casing. Isolating physics variables into separate, independent tests creates dangerous predictive blind spots. Only coupled multiphysics can reveal the true overlapping operational stresses that a physical design will face in the field. Processing nonlinear multiphysics contact models across high-density meshes generates a massive mathematical payload. To manage this, ADINA relies on high-performance solvers that are optimized specifically to process huge arrays of equations with strict speed and unwavering precision. Yet, immense computational power holds little practical value if the software interface is too convoluted for an engineering team to efficiently operate. ADINA features a graphical interface designed to simplify the exact definition of complex boundary conditions and specific material assignments, drastically reducing the time required to properly set up a model. Once solvers conclude their run, post-processing tools, like this 3D contour plot, translate raw numerical data into clear, actionable visualizations of stress distribution and material deformation. Combining optimized high-performance solvers with intuitive post-processing workflows transforms dense theoretical mathematics into a highly practical, deadline-driven engineering tool. The true advantage of ADINA's element library and sophisticated solvers lies in their exact scalability. The very same mathematical algorithms used to calculate microscopic friction on a single gear tooth are directly deployed to evaluate massive seismic loads on concrete dams, steel suspension bridges, and commercial high-rises. Navigating computational mechanics at this level of fidelity inherently comes with a necessary learning curve. However, the software ecosystem is backed by comprehensive documentation, detailed technical manuals, and a highly active technical support network. This carefully maintained infrastructure bridges the knowledge gap, making high-fidelity structural analysis entirely accessible to both seasoned computational researchers and new structural analysts alike. Ultimately, ADINA operates as a unified ecosystem, integrating specialized analysis features into a single workspace. It seamlessly connects the baseline mathematical mesh to complex nonlinear contact mechanics, dynamic external vibrations, and coupled multiphysics interactions. When a massive modern suspension bridge stands entirely firm against the buffeting force of intense gale force winds, it demonstrates the reliability of predictive computational modeling. High-fidelity engineering demands that we model reality exactly as it is, complex, deeply dynamic, and entirely nonlinear. ADINA provides the architecture to achieve exactly that.